roughly speaking, what would this curve look like? All right, and this is going to be a real rough sketch. All right, unfortunately, below. So from -4 to -2, -4 to -2, and then at -2 it does something weird, and then up to 4, and then from 4 to 6. Over these regions, it has different definitions. From -4 to -2, it is a line with slope -4 and y-intercept -7. We don't have to graph the whole line, right? If we wanted to graph the whole line, it would look something like that, roughly speaking, right? It has a big negative y-intercept and a negative slope. But we don't have to graph that whole line. Honestly, we just have to graph 2 points. We have to plug in 4, and we have to plug in -2. Now, because -2 is not in the domain, notice that it has a parenthesis, not a bracket. Sorry, I know that you can't see that. Because -2 is not in the domain, notice it has a parenthesis, not a bracket. We know that that is not actually going to be, on the line. All right, so at that point, we're going to draw an open circle. So plugging 4 into -4x minus 17, that would be -16 minus 7, so that's -23. Way down here. Whoa, wait, hold on a second. Oh, sorry. Woo! -4 times -4 is positive 16. My bad. I'm sorry. So positive 16 minus 7, that is 9. It's around here. All right. Plugging in -2 times -4, that's positive 8 minus 7. That is a 1. So we'll draw an open circle here and connect the dots with a line. But what is actually going on at -2? We see that the graph has a height of 6. All right. Then between -2 and 4, it has this parabola. Now, this parabola, very importantly, it opens upward because its leading coefficient is positive. It's a quarter. But what's more is that really we know kind of what this parabola looks like. It's just some scaled version of x squared. That means that it's either smushed vertically or stretched vertically or smushed horizontally or stretched horizontally. In this particular case, we are multiplying it on the outside of the argument, so that would be a vertical stretch or smush. We are multiplying it by a factor of 1/4, which is less than 1, so that's a vertical smush, which, by the way, is more or less the same thing as a horizontal stretch in this case, right? You press something down enough and it's going to go out at its sides. And that's basically what's going on here. Really, we just have to think of 3 important points: what's happening at 2, what's happening at 0, and what's happening at 4, and then just kind of roughly try to sketch them with a parabolic shape. Plug in -2, right, and you get 4 over 4, that's 1. It would in fact be right here. Plugging in 0, you get 0. Plug in 4, you get 4, which is a little bit less than 6. All right, and that is in the domain there. All right, but then from 4 to 6, it is just a horizontal line at height 6. Sorry, it won't draw sometimes. Oh, weird. Whoa, what's going on? Oh, it's because I accidentally hit that rectangle thing with my pinky. My bad. How do I go back to the regular free draw? That's it. All right. So right here, this is at height 4. All right. This is roughly what your curve should look like. All right. Line, nice straight line. Nice curvy parabola. Another straight line. There should be open circles here and there. We should be having a solid dot here. All right. And now, really, the next part of the question just comes down to certain types of, well, I'm going to skip part A for a moment. Because really, I want to revisit the definitions of jump discontinuity and removable. I'm not really sure what kind of mnemonic devices we're using to try to commit these to memory, but a jump discontinuity is real easy to look for because the graph is literally making a jump in space. It is jumping from one height, whoop, up to another. All right, or sometimes the jump discontinuity jumps down, but in this case it jumps up. All right, so that's what a jump discontinuity means. It means there's a literal vertical jump in the height of the graph, whereas a removable discontinuity is something that, were you to just fill in the hole, suddenly the graph would become continuous. I mean, if we were to fill in that hole, suddenly it would stop being a function because it would fail to pass the vertical line test. But, if we got rid of this point and filled in this hole, then the discontinuity would be removed. All right, so the answers to B and C, respectively, the jump discontinuity is at x equals 4, and the removable discontinuity, hold on, let me hit back a few times. All right, and the removable discontinuity is at x equals -2. All right, so this is graphing the function. That really didn't have a letter. All right, but A will have 4 different answers. 1, 2, 3, 4. B, the jump discontinuity is at x equals 4. And C, the removable is at x equals -2. Sorry, there was schmutz on my tablet. All right. So now let's go back to part A. All right. Part A is all about limits. Let me zoom in a little bit for you. 1, 2. I'm just counting so that I can unzoom once I'm done talking about these. All right. And I'm mostly going to refer to the graph that I have right here. Okay. So the limit as x approaches -2. Now this is a two-sided limit, so we have to think about both one-sided limits. And indeed, as we approach -2 from either side, the height from either side approaches +1. All right. So the limit here does exist, and it is equal to 1. All right. That was part 1. Part 2 is asking for f of -2. That, unfortunately, is not equal to 1. That is equal to 6. All right? And so, because the answers to 1 and 2 differ, that means that this function's not continuous at -2. That's not one of the questions on the test, but I'm just mentioning that. All right? Limit as x goes to 4 from the left and from the right. All right? These are parts 3 and 4, respectively. And both of these, again, limits exist as we approach 4 from the left or from below. That's what that minus sign means, right? It is approaching a height of 4, okay? So this answer is going to be 4. Whereas as we approach from the right-hand side, right, what height are we approaching here? 6, okay? So these are your answers to number 1. All right, that's what the picture looks like, more or less. The limit as x approaches -2 is 1. F of -2 is 6. The limit as x approaches 4 from below is 4, and from above is 6. There's a jump discontinuity at x equals 4, and a removable discontinuity at x equals 6. 1, 2. All right, on to the next page. Obviously, if at any moments in this talk you need to pause, obviously feel free to pause. Generally speaking, I'm going to turn to the next page before I erase what's on my whiteboard. All right? Let's focus on number 2 next. Okay? So, now I'm going to clear my whiteboard. All right, number 2 is asking for 4 different limits. Limit part A. Let's see. Can I do this? By the way, most of the time, your first, and I mean, I know that you don't need me to tell you this. Most of the time, your first trick should be direct substitution. All right. Limit as x goes to 3 of 2 sine pi x over 12. So this one does work with direct substitution. This is literally just 2 times the sine of 3 pi over 12. But, you know, what's that equal to? This is equal to sine pi over 4, which is root 2 over 2. So if we multiply that by 2, right, what do we get in the end? We get square root 2. And that is the answer to 2a. I guess you can't really read it up there. Sorry. To 2a. All right? So that's how you do it. Direct sub. Direct sub is all. Next. To b. Or not to be. Anywho, we try direct sub again, and I mean, it's going to work out, right? I can already tell you it's going to work out because I know that the denominator, when I plug in 3, is not equal to 0. So even if the numerator gives us 0, that means that the limit's just equal to 0, okay? But this limit, I'm not even going to write the word. I'm not going to write the fact that I'm doing the limit. I'm just going to evaluate it immediately by direct sub. All right, this is just 2 times 3 squared minus 5 times 3 plus 2 over 3 plus 2. And that is equal to, what, 18 minus 15 plus 2 over 5. That's square root of 1, or 1. You know, now that I'm actually working this out, I do believe that at least 3 out of the 4 of these were direct substitution. Okay, to C. Or not to C. All right, bud, that joke only works once. Here, again, we can do direct sub, but it all kind of falls apart when you just remember that log base b of 1 for any base b is always equal to 0. Remembering, of course, that b here must be a positive number, not equal to 1. Sorry. I don't know why. I said those two things at once, and it kind of got mixed in my brain. It's not greater than 1. It could be less than 1. Just, you know, not less than 0. Anywho, so when we do direct sub on 2c, what do we get? We get 2 times 1 cubed minus 5 times 1, and that's 3, right? No, I'm sorry, it's negative 3, right? Because we're not cubing the 2. So it'll be 2 times 1 minus 5, and that's negative 3. But log base 2 of 1, this is 0. So the whole thing is 0. So far, the answers to part 2 were square root 2, 1, and 0. Let us see what the last one was. Oh, this one, finally, we have to do something that we, you know, learn the tools of calculus for. Because we tried direct sub on this one, and you will indeed get, well, not necessarily 0 over 0. Hold on, let me check. 4 plus, yeah, you'll get 0 over 0. I would factor the numerator, and I would try to use our useful rule. All right, x squared, oof, let's actually write x squared, huh? X squared minus, or plus rather, 3x minus 10, all over x minus 2. All right, I'm looking for two numbers that add to positive 3, multiply to negative 10. If I can help it, it would be lovely if one of them was minus 2. And indeed, if I factor the top, as x plus 5 times x minus 2, it works out just fine. And it's never a bad idea to check our work. Actually foiling this out first, outer, inner, last, and then inner and outer would combine to positive 3x, so we're all good. Now, using the useful rule, right, this equals the limit as x goes to 2 of just x plus 5, right? And that is, through direct sub, just 7. Okay? So, in summary, the answers to part 2, again, were square root 2, 1, 0, and 7. These were the answers to part 2, to question 2, rather, not part 2. I don't know why I'm using that. I have literally a trash can button. All right, let's move on to number 3. Number 3 was just these 2 parts. All right, 2 more limits. These ones are at infinity. 3a was a little bit of a tricky question, because notice that the limit is as x goes to negative infinity. All right, and what's more is that in the denominator, we see a radical. Okay, so when we try that trick where we multiply the top and bottom by the highest power, divide the top and bottom by the highest power of x you find in the denominator, we're not going to just be able to distribute 1 over x, right? Notice the highest power of x in the denominator is x. We're not going to just be able to distribute a 1 over x through 9x squared minus 2x plus 1, because all of that is under a radical. At best, we will be able to rewrite the thing like this. All right, I have multiplied the top and bottom. Ah, shucks. All right, sorry. Oh, wait. There we go. I have multiplied the top and bottom by the highest power of x I found in the denominator, where the denominator was 2 minus 3x, and the numerator was square root of 9x squared minus 2x plus 1. All right, but the issue here is that whereas this 1 over x does distribute just fine over this difference in the denominator, all right, I cannot distribute it here because of this radical. So what do I need to do? I need to replace it with something that has its own radical. And in most cases, that is done by setting x squared, or x rather, equal to the square root of x squared. But I want to point out that x is going towards negative infinity. All right, so x in particular has to be thought of as negative numbers that are getting more and more negative. All right, and this simply is not true for negative numbers. Take negative 3, for instance. Negative 3 squared is 9, and the square root of 9 is 3, not negative 3. All right, so what do we do to remedy this for negative numbers? Well, for negative numbers, we can't set x equal to positive square root of x squared. So we instead have to use the fact that x is equal to negative the square root of x squared. All right, so I can distribute in the bottom just fine. So this is equal to the limit as x goes to negative infinity. In the bottom, I get 2 over x minus 3. But in the top, I have to replace this 1 over x with negative 1 over the square root of x squared. Sorry. This stylus that I'm using is not the most sensitive stylus. There we go. All right, now I can in fact distribute that in there. All right, but notice the importance of what has happened. A minus sign has been introduced where there was none before. All right, that is significant, and it is because we are approaching negative infinity. And in order to rewrite x as something involving a radical, we couldn't just say that x is equal to square root of x squared. X is equal to negative square root of x squared for negative numbers. Now I can distribute this over that. All right, and I get that this is equal to the limit as x goes to negative infinity, my bad, of negative square root of 9x squared divided by x squared is just 9, minus 2 over x plus 1 over x squared equals 2 over x minus 3. All right. So this is not direct substitution, what I'm about to do. All right. This is just using the fact that as x grows without bound, when x is seen in the denominator, that shrinks. All right. So all of these things, minus 2x, 1 over x squared, 2 over x, all of those go away. And this is just equal to negative square root of 9 over 3, negative 3. But that's just negative 3 over negative 3, or 1. Aha! I knew I shouldn't have moved it down. All right. So, that is how you would do this first limit. Okay. I would pause here if you have any questions. And I'm going to erase. All right. Part B. Part B. Okay, so again, we just divide the top and bottom by the highest power of x found in the denominator. In this one, we're just going to get 0. How do I know we're going to get 0? So easily, so quickly? Well, I know we're going to get 0 because the highest power of x is found in the denominator. So we divide both the top and bottom by the highest power of x found in the denominator. What will happen to the numerator is it will become 2 over x squared minus 4 over x to the 4th plus 2 over x to the 5th all over 4 minus 7 over x to the 5th. And each and every one of these terms will go to 0. So this whole thing, the limit as x goes to infinity, sorry, we don't need to write that once we've actually evaluated the limit, will be 0 over 4, or 0. Okay? So the answers to this one were 1 and 0. So in general, limit of g of x, limit as, not x, sorry, limit as h goes to 0 of g of x plus h minus g of x all over h. Okay? And here, I'll be perfectly honest, I can't actually read what that says. That says 2x squared minus 5. Fabulous. All right. So this is the limit as h goes to 0 of, so rather than plugging x in, we'll plug in x plus h. This will be 2 times x plus h, quantity squared, minus 5. This is g of x plus h. All right. Minus g of x. All right, so that's not going to be a 2x squared minus 5, but a minus 2x squared plus 5. All right, and this, including the signs and all of that, is minus gx. Okay, minus gx. All over h. So we first notice that the 5s, they cancel, right? And we've still got a minus 2x squared here, but let's actually FOIL out x plus h and then distribute the 2. So this is the limit as h goes to 0 So I'm going to kind of do that step all at once. This would be 2x squared. All right, and from the foiling, you'd get xh plus another xh. That's 2xh, but multiplying it by yet another 2, that would be 4xh. And then at the end, plus h squared, but don't forget to multiply it by the 2, minus the 2x squared. Whoopsie. Yeah, see, it gets a little wonky when it gets towards the end of the tablet. Yeah, hold on. All right, have it your way, tablet. Minus 2x squared. This goes right there. Sorry. All over h. Right? 2x squared and the 2x squared, they cancel. Okay? And we notice that everything that's left has at least one factor of h. 2h squared, of course, has two factors of h. That's 2 times h times h. So I'm going to basically do the reverse of distributing. I'm going to pull that h out. Okay? And I'll just be left with 4x plus 2h. Okay, that's what this whole thing equals. But notice, again, we've got these similar terms of h. The useful rule tells us that this is equal to the limit as h goes to 0 of 4x plus 2h. But, you know, we can figure out that limit just through direct substitution. That would just be 4x. Technically, I skipped the step where I wrote that this is equal. Okay, I'll write it. 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 This is equal to the limit. Oh, God. At this part of the board, it's going to get all messed up. All right, I'm just going to erase some stuff. You can rewind, do anything you'd like at this point. But this is equal to the limit as h goes to 0 of 4x plus 2h. I mean, direct sub, the 2h will go away. This is equal to 4x. Okay? This one requires you to find the equation of a tangent line at a certain point on the graph. All right? Give the equation of the line tangent to the graph of 3 over x at the point 3, 1. We have a point on the line. All we need to do is find the slope. And the slope of the line at that point, slope will be f prime of 3. All right? Because we are looking at the point 3 comma f of 3, right? F of 3 here is indeed 1. 3 divided by 3, that's 1. Right? But we need to figure out what the heck f prime is. And we can do that just by finding the definition, or we can find the derivative using, you know, the definition of the derivative. We could even just find the slope directly by calculating the limit as x goes to 3 of 3 over x minus 1 over x minus 3. Okay? This is f of x minus f of 3 over x minus 3. Right? This is slope of a tangent line. Here you'd find the common denominator. All right, and this would become 3 over x minus x over x all over x minus 3. This is equal to the limit as x goes to 3. I'm missing that here. So here in the numerator, we'd have 3 minus x. Dividing by x is the same as multiplying by its reciprocal, so we can just move that downstairs. And I want to point out that this 3 minus x, that's just equal to negative x minus 3. Right? So by the useful rule, this limit is equal to the limit as x goes to 3 of, not forgetting about this negative part, negative 1 over x. And, you know, you just plug in the 3 now, and this limit is negative 1/3. Okay? Let's pause for a moment. Look at what we've done here. We calculated the derivative from, well, we didn't calculate the derivative from scratch. We calculated the slope of the line tangent to the graph at 3, 1 from scratch. And we got that slope is negative 1/3. We could have also just found the derivative. I mean, f of x is equal to 3 over x is equal to 3 times x to the negative 1. So f prime of x would be negative 3x to the negative 2, which one should rewrite as negative 3 over x squared. Actually, plugging in 3 then gives negative 3 over 9, or hey, negative 1/3, just like we found it. All right, either way you do it, that's the slope that you get. So we have a point on the line, which is 3, 1. We have a slope, hold on, sorry. We have a slope, which is negative 1/3. The point on the line is 3, 1. We all know how to write this in point-slope form, but y equals mx plus b is slope-intercept form, so we need to do a little bit of algebra to get it to look like that. Y minus 1 equals negative 1/3 times x minus 3. That on the right-hand side becomes negative 1/3 x plus 1 equals y minus 1, and we get y equals negative 1/3 x plus 2. All right? Anywho, if you have questions, comments, concerns, come see me during office hours. I'll see ya.